Hi, good morning, everyone. So, we will do the speech synthesis. That means basically text to speech. Last week we have done speech to text, right? So, speech to text mean, for example, when you click this one, whatever you say, it will be get typed over here. So, that means you are talking and which is converted into a text. So you can see in the chatbot that we have implemented that we have added this speech to text module in the backend. So it listens to you and it create that thing. Now, what is meant by text to speech? Text to speech option is over here in our chatbot. If you go here, now what is happening is this testing is being read, right? Increasing the batch size to 1,000 will likely increasing the training time and more. So this is called text to speech, right? So in the previous example, that's what we are going to learn today. In the previous example, we have created the MEL spectrogram, right? From the audio signal, we know that time domain signal is the thing that we talk. When you listen, we can plot it in the time domain signal. So with the time domain signal, we can extract the feature using the Fourier transform. What are the frequencies involved in that time domain signal? So that is called frequency spectrum. So if we use the time domain spectrum or the frequency domain spectrum, we are going to lose certain information. If we use the time domain spectrum, we are going to lose the characteristic of frequency domain spectrum. If you are going to use the frequency domain spectrum as a character or a data to train the model, we are going to lose the time domain information. So to do both the information at the same time, take it into consideration, we came up with another solution called spectrogram. So in give me a second, sorry about that. So when we did the training for the voice to text model or speech to text model, the input we recorded and our voice is converted into a MEL spectrogram, right? Spectrogram. MEL spectrogram means it's another version of the spectrogram. So spectrogram is just take all the frequencies into consideration and plot. MEL spectrogram means it has an audio range of frequency. So it's adjust the spectrogram according to the MEL curve. So that's we have seen in the voice identification or speaker identification tutorial. So the MEL spectrogram is the input for our neural network model and the output is a text, right? So we have collected the recorded audio with the text and we have trained the model. MEL spectrogram is the input and the output is going to be the text. So that's how the speech to text is done. So now the text to speech means what? We have to read the text and we have to get the output as an audio. So that is called text to speech. So in that case, in general, what do you think? What should be the input and what should be the output for the model? So earlier, carefully listen. For the speech to text, our input is the audio signal spectrogram and the output is the text. So now we are going to do text to speech. So in that case, what will be the input and what will be the output? Yes, input text, output is speech. But we can't generate the speech directly. So what we can do is we can generate the spectrogram. If we have the spectrogram, we can convert that spectrogram into a speech signal. You get it now? You get it, right? So now this is going to be a challenging task. Even though the speech to text is there from 2001 time from Google, right? It's introduced, but it's like a robotic voice. If you see, go to this thing again, and I'm going to play it out. Let me see. Increasing the batch size to 10,000 will increase the training time. Oh, it's a computational, it's a little different, right? So that means you will understand why it's happening, right? So that we don't talk like that. We talk in a natural way. But when we listen to the text to speech model, it's really different. So this is an old type of text to speech way. So after 2017, and it's a lightweight because we have to speak it in the real time. So after the text come, we have to speak it out. So after 2017, the transformer model, that is the huge jump for AI, right? So earlier we were using neural network, deep learning, recurrent neural network, a lot of type of neural network. After the transformer came, all these neural networks got suppressed because the transformer architecture is the backbone of ChatGPT, right? So after the transformer came, this text to speech model was trained on the transformer architecture, right? So in this class, we are not going to go into transformer architecture because we do not know what is transformer architecture. So next class, I will be able to explain you what is a transformer, what is the backbone of ChatGPT, or upcoming lectures we will learn. After that, you will understand how to do that training. It's a little bit different than the neural network, right? Because it has a memory feature, it has an encoding, it has a decoding feature, it have attention layer, like different architecture. Neural network, you know, input, dense layer, convolution network, max pooling, and dense layer output, right? So, but it's not like that now. It's going to be totally different. So later, after 2017, all these text-to-speech model were trained on transformer model architecture. That means it's an AI model, but it's a different AI model compared to the neural network that we have built in the past. So later on, now the text-to-speech is more realistic. So that you have seen here is not a transformer based in the chatbot. It's just a normal earlier version of this text to speech. But nowadays, the real human like spectrum came up, the real cloning. I talk and I can convert my voice output as Obama's voice output. So those things are possible with the new transformer architectural manner. So we will not discuss that one, but we will discuss the typical neural network AI based model to do the training, but the same concept. Only the architecture of the model is going to vary for the transformer. Other than that, input, making the audio clips and the feature engineering, everything is going to be the same. All right. So now we go here. So what is speech to text? So text to speech, at its essence, TTS, text to speech, is a synthesis process that converts text into spoken words. So this process had a rich historical development evolving from simplex text reading machines to the sophisticated system we use today. Today, the TTS relies on advanced deep learning algorithms. That means it's a transformer architecture that they are talking, and neural networks allowing for the development of more natural and expressive voices. So now the issue over here in the chatbot, it just reads. It does not carry the emotion. But nowadays, it carries the emotion as well. Right? It understands the text and it put the emotion in that while reading. So now, earlier days, if you take the Amazon books, have you seen the Amazon video books? They released a tablet and you can download the books and you can read the books. Or you can put it to audio, right? It will read it for you. So that kind of earlier voices, like it just read. If is it going to read, it will do like this. At its essence, TTS is a synthesis process that converts text into spoken words. Something like that. Tame tone, nothing. Flat tone. But nowadays, it's like completely carry the emotion because of the transformer architectures. At its essence, TTS is a synthesis process that kind of tone variation, emotion variation. If you see a sad text, it carry the sad tone. If you are basically for the kids, if they are telling a story, certain points they have to enhance the voice and reduce the voice. All these things can be done now because of this transformer architecture, right? So the process behind text to speech technology is a series of complex yet fascinating steps. Initially, the system performed text analysis, dissecting sentences and words to understand their structure and meaning. This followed by linguistic processing, where the text is converted into phenomena. So think of it as translating the written word into a language that machines can understand and speak. So this cat, have you seen this library? Cat? Cat. Have you seen it? If you go to Google, for example, Google, okay, maybe you type something. See, description comes up over here, but this is something called phonemes, right? So this is how you pronounce the word. If you play it, right? So this is the thing. That's so one thing what we do is we break it into phonemes, right? And we read them. So the smaller units of sound in each piece. English have 44 phonemes. So we have 24 letters, but 44 phonemes in English or sounds. So the word cat and phone both have 3 phonemes. Phone, phone, cat, cat. But THONE, 1, 2, 3, 4, 5 letters, 3 phonemes. Right? So that we can break it into that categories, right? So subsequently, a linguistic processing component interprets the analyzed text, assessing appropriate and rhythm and intonation to create a natural flow. So that's how the AI model is going to break it. So this is called TTS engine. So welcome to the world of speech synthesis. Natural language processing is processed. So raw text data is given, tag text data is given, then tag phonemes is given, context, then synthesis piece. So finally, we are taking that thing. So this is one type of architecture. If you ask me, is this the architecture only? No. There are several transformer architectures available to carry the tone, to carry the voice emotion, to read speech, like different ways, right? But we are going to learn about that today, which is going to be the very basic concept for that thing. If you know that, rest of the things only going to vary is the architecture of the model. Other than that, input and output is going to be the same, right? So, right. So you can read it through that, whatever I have explained over here. So now let me know if we want to train a neural network for text to speech, what are the data that we need? Pronunciation in which format? Yes. Phonemes is one way. That is a way, but that is not only needed over there. Today we are not going to use the phenome. We will use it a little different way. So the input we need is the text. That is clear, right? So we need text. Okay. So the output that we need is the voice. So that means we are going to do a supervised machine learning or AI training. If is it going to be a supervised AI training, what is going to be the input and what is going to be the output? So basically, you are going to put the text as an input. Output is going to be the spectrogram, right? And that spectrogram is going to be compared with your original spectrogram. Error will be calculated and it will be propagated back to the text. So that's how the training is going to happen. Earlier days, we give the spectrogram, predicted the output. We give the spectrogram, predicted the voice. We give the spectrogram, predicted the text, right? But now it's going to get break. We are going to give the word or text and going to predict the histogram. And that histogram is going to be compared with the input spectrogram corresponding to the input text. Error will be calculated, propagated back, and the training is going to happen. So this is one. So now another issue I'm going to ask. So The spectrogram really depends on the voice of the person, because I have a different frequency. You have a different frequency. So if you read this paragraph, imagine tuning written words into spoken language. That sounds just like a person talking. If you read this one, same letter, same text, it's going to be completely different, because your voice is completely different, your frequency is different, your tone is going to be completely different. That means you are going to have a certain voice. So that is going to be different from mine. So can I do multiple reading voices for text? It is possible, but it's not easy, right? It is possible in transformer architecture multiple way. Here we are going to use only one speaker spoke certain text, reading a book or something, and we recorded that thing, break it into small audio clips along with the text. So that is going to be our input. For example, we ask a person to read a textbook, recorded the whole audio for maybe 1 hour, 2 hour, and break it into small pieces. And we take the relevant text also. So if I am reading, imagine tuning written words into spoken language, that sounds like a person talking. So if I read it, I record this text and the audio clip. One clip. Second clip. This isn't a futuristic idea. It's the reality shaped by text-to-speech technology. Second text, second audio clip. TTS have woven itself into fabric of our daily experiences. So third text and third audio clip. Like that, the same person, we ask her to read multiple text to speech, and we have recorded it and we have saved it. Okay. So that is the data that we are going to use. So how many data we need to do the processing? For this, we need millions of data, right? Basically to get it to a very good level. But if we do millions of data, definitely we cannot perform the training in the Google Colab within a day. It needs an expensive training. So we will use 1,000 data for today, and we will learn the concept. We will try to play the audio. Definitely, it's not going to come back from the text, right? Because the 1,000 data is not enough. And we have to make sure all the voices are heard, right? All the words are in the text, right? We have 1,000 means we don't know how many words are missed. So certain words should be heard to the model, what we are going to train. But therefore, the output is the model is not going to be accurate. But we will load another tutorial and show pre-trained model, how we can use that in the Python, right? That's the way that they have trained. But we will not do the training up to that level, because we cannot in the class, and our Google Colab environment will crash if we do a lot of training, right? It will reset. I tried multiple times yesterday, crashed, and finally I reduced the sample size to 1,000. Now it's somewhat working. I don't know whether it's crashed today or not, but it'll work. Okay, so that's the thing. So now we will start the processing. So the people who came little late, briefly I will explain. Today we are going to learn about text to speech, right? Earlier last week, speech to text. So the voice input that we have given, and we have predicted the text last week, right? For that, what we have given the input is the voice, and the output is the text. So the predicted text we compare with our input text, and we get the error propagation. So that's how this thing now. So input voice, that how we gave last time, we gave it as a spectrum. Okay. Para, you have to mute Suranga. His mic is unmuted. Para, could you please mute Suranga Varshapam? Okay, thank you. All right. So the input to the text to speech, we have to give the input as a text. Output is a speech, right? So that means our input is going to be text, and the output is going to be a spectrogram, and we are going to reconstruct the audio using the spectrogram. That is a whole task. Okay. So I found out certain data, luckily, which have recorded a certain text and a voice clip, certain text and a voice clip with the same person, right? Which is in the Kaggle. So we will use that one as we did it last time. So first we will install the required library. We need the TensorFlow because we are going to use the TensorFlow for this tutorial. And NumPy, you know, and Librosa is the thing. Last time also we have installed Librosa to process audio signals, right? So all the three we are aware of this thing. So we are going to run that thing. So run it out. It will take a while because the TensorFlow and the Librosa might maybe not much time, couple of seconds. Okay, make sure you have connected to T4 engine because this is a like very intensive training task. So it might crash if you are just using the RAM. So the T4 engine should be mentioned over here, GPU, right? Okay, now we have installed the libraries, required libraries. After that, we are going to download the data. So we know we have performed the same downloading step last time. First step, we have to go to our downloads, right? And upload the Kaggle file. We already have downloaded last week. The same Kaggle file you can upload. If you do not have the Kaggle file, go to the last session, download the Kaggle and upload it. Last session, AII have the Kaggle of mine. So you can upload that and download it, okay? Okay, I will upload this Kaggle to my platform. Then I will do the part. This is the fourth time we are downloading the data from Kaggle. So I hope I don't want to do it again. So that file is there, drag and drop here, then run it. So this is an open source data. Unlike last time, we used a closed data. So we have to approve certain things. This is open source. So we don't want to worry too much. We can just directly download. So I have installed the Kaggle and I have uploaded the kaggle.json file over here. And I'm going to configure the Kaggle with the API. After that, I'm going to download the data. So that is from this LJ speech data set, right? So this is the link. You can copy and see. I'll explain the Kaggle data set, okay? So, yeah. So this is the speech data set. So this is a public domain speech data set consisting of 13,100 short audio clips of a single speaker reading passages from 7 non-fiction books. 7 non-fiction books. She just read the text. We recorded it, break it into pieces. So transcription is provided for each clip. Clips varies in length from 1 to 10 seconds and have a total length of approximately 24 hours of clip. So we have broken into small pieces. Broken pieces were there. Even you can do this audio description here. What you can do is you take a book, read it in your own tone. If you want your own tone, read it in your own tone, own voice, record 2 hour or 24 hours radio recording. It's not possible. Break it into pieces using audio processing, get the relevant text using Google transcription. Then you save the data. It's going to take time. So we are not going to use that. We will use our save open domain data to the task. Put it for downloading and we'll go here. So make sure you put it to the downloading option. It's going to take a while. So I'll explain what is the data set is. Okay. So it's downloading. So we have 13,100 short clips of audio. The metadata has the what are the audio clips, what file with the audio clip. For example, if I load it, this is the metadata. So I know LJ 001003. right? LJ 001 001. So that actually says in the only sense with which we are present concerned. So some reading is there, differs from most if like something like that. So this is the text it read. So LJ, this is the audio file name, and this is the thing. By similar processes, although the Chinese took impression from wood blocks and which were the immediate predecessors of blah 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 blah. You know, these are an example of fine trauma, blah blah blah. So there are a lot of stuff over here, right? In the metadata. So metadata means what is the file name and what are the texts that they have read as an Excel file, right? So the audio file is inside this waves folder. So I can play a wave folder. Something like that. You get it, right? So this is, and the metadata presents the same text. So these are the data that we need actually. So here, if you go here, printing is the only sense with which we are at present concerned. The same thing is read, right? So we'll go to the wave file and maybe play another audio. So maybe 30th voice. So if you see, all these voices are from one person. Why? We don't want to confuse the model. Because if one person, the spectrogram is going to have the same frequency, kind of same thing, same speed of the thing. So we can, there is less chance to confuse the model while training. If multiple speakers speaks, the spectrogram also varies and the models get harder to train, right? For example, you take some images of a cat and you train cat, 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 cat. And a dog, 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 right? Totally fine. The model will be able to understand this is a cat and a dog. In the middle, you take a cat which looks like a dog and you put as a cat, then the model get confuses while learning, right? So the same approach. So the same person, same voice, less confusion. Multiple people, multiple text, multiple voices. The model spectrogram, it can do the training, but the architecture should be very complicated to identify those things. So if you want to have multiple voices, easier way, record multiple voices, train separately and combine that thing. A person go and select certain voices. Even we have that option over here. So you can go here and select Zira. Just say. There is an issue. Both are the same agent, but we can select the voice. So what happens is that voice is trained by this girl. Another voice is trained, recorded from the other girl. So other guy. So there is something happening in our thing. I need to check it out. So like that, here we are going to have the data set. So now the data set is downloaded already. So we'll go and extract the time file. So you can see it as a zip file. It's downloaded. So we know we have to extract the zip file. So we will extract the zip file over here. So then it's going to extract all the things. It's going to take a while. So because it downloads as a zip file, right? And also there is another thing for the metadata. So it has the metadata inside, but this is another metadata. This format also good, 13,700 printing in the only sense with the same thing. We will also, it's a same audio, but the metadata we are going to download it separately because the metadata that we have over there have some issues, right? The same thing, same audio, same thing, but only we are going to download the metadata over here. So now we are still getting it out. Metadata means the text which is spoken. That's the thing, right? So the input is going to be the text for us output is going to be the spectrogram. The spectrogram is going to be constructed based on your text input. Then the spectrogram is going to be converted into an audio. If we can convert an audio into a spectrogram, we can convert the spectrogram into an audio band. There is no harm, right? So then we are going to do that. So now we have extracted all the wave files. You can see there are a lot of wave file over here. We can just scroll it down, keep on going. 13,000 something is there. So that we have downloaded. So now we will download the metadata. It will be quick separately. It's just some KBs. Again, we will unzip that one. So you can see the metadata will be here. Is that clear? Have you done this one? Okay. If everyone is completed, then we will go to the next step because we have downloaded the data. Have you downloaded it? Yeah. Good. All good, ne? Okay. So we will move on to the second thing. So now what we will do is inside this folder, right? There are 13,000 and certain things. How much? 13,100 data are there here. 13,100 data are here. And we are going to load the certain file over here. LJ001, L0001 wave, and we are going to play it. Right? If you play it out, it will go to that thing and let's play. Right. If you go to the LJ speech, printing in the only sense which we are at present concerned differs from most if not from all something. Right. So this is the metadata. Clear? So now we'll go to the second thing and play it. I'm going to change the name over here and change it. Go to that thing. In being comparatively modern. Right? So go and change it to number 3. Clear? That's clear, right? Cool. So now we have done that, loaded the data. So now what we will do is, we'll plot a certain path. Okay, we'll take the first signal. I'm loading the first signal, audio clip, and I'm going to plot the time domain and frequency domain plot. If you see here, this is the time domain plot, right? And this is the frequency domain plot. So frequency mean what? Using the fast Fourier transform. So as I said, we have to get the features from the audio signal. So from an audio signal, one is a frequency feature, other thing is the time domain feature. Combining both together, we can get the spectrogram. So that's the input that we have used the past voice identification, speech to text, everything. Now we are going to use the same, but the output is going to be the spectrogram. Input is going to be the text, right? Spectrogram means basically we can convert it into a voice. So now if you see here, let's load the second one and see how the speech and frequency signal varies. If you see the frequencies, speech might vary, but if you see the frequency, she has the voice frequency around 2000. The spike is around in this range, like maybe around 200 hertz, right? So we will go to the third one. The time domain signal will completely vary because the tone is varying, but you can see the peak is around 2000. So that means the frequency of a person is more or less consistent. Background noises are here. You can see this part is little up, the background noises. They purposefully created these background noises, right? To make sure the model is not getting confused, right? So the background noise is purposefully added to each audio clip. But the person voice is lying in between this frequency range. Let's go to the fourth audio clip. because most of the human voices are within that range, 800 somewhere. See, in that thing we are having the speed. So that's why it's always good to have one person to read. We are going to read. So the output will be in her voice, whatever we are going to get today. So now fine. Okay, good. So now time domain spectrum is this one. Frequency domain spectrum is this one. But we don't care these both. What we need is a spectrogram, right? So let's create the spectrogram for the first audio clip, right? So once you play it, so text to speech where the applications are applied. So one I showed the chatbot, right? So whatever the Gemini or Google, anything they use this text to speech. Even in the Word document, read text to speech. And nowadays, I found an app which they have trained a model to read research papers, right? General text is different than the research paper. Why? Because research paper contains equations. So if you put to a general text model that you are going to read a kind of a simple way of these things, and if you ask a certain number to read, like equation to read, it won't read. It will say sigma 1 plus 1, 2, 3, like plus sign. It will say plus sign. Instead of plus, it will say plus sign. Something. So that's not the way to read the research paper. So the research paper have equation. So what they have done is that people have collected the data from a person by reading thousands of research papers. Sigma, this function is defined as sigma, or in total of, you don't want to say sigma, right? In total of adding the numbers of from here to here, right? So that way they have read the research papers and they have trained the model to read that in that with the voice clips and the text. Then the model learn to read the research, right? So now they are selling it up. Okay, as an MSc student, PhD student, I saw a lot of things. You can listen and joke to the research paper. You can run or purchase certain things and listen to that research paper. So I didn't have that task when I was a PhD student. We had to read close to 300, 400 papers to come up with an idea to do the research. So if that was there, it might be faster. But I didn't listen yet, but that's the way. If you want to read a Chinese script, you can't use an English language at all, right? Because we have seen when I talk singular language to my speech to text model, IBON, it take IBAN something because it cannot. It cannot. If you want to talk singular language to text, you have to train a model particularly to do that singular thing. With the English, it might do a little bit okay by reading that singular text to English conversion, and reading the English conversion might be possible using these phenoms, right? What we have seen, but it's not accurate. It will be pronunciation will be totally wrong. So better thing, ask a person to read singular, collect the singular text, and do the training, right? Then that's the easiest way. So this is the MEL spectrogram. You can see in a different color. We have 8,192 frequencies, but we have seen at the bottom 512 frequencies. The magnitude of the frequency is higher, right? We can see here also, right? See, around close to 500. The magnitude of the frequency is higher. Higher means the dark color, dark orange. So the dark orange here is 0 dB. All are minus. Minus means less than 0 in decibels, right? Decibel means basically 20 log magnitude. 20 log, right? Log magnitude. So that is the decibel thing. So to visualize it in that thing, we just plot that one. So this is going to be the output that we are going to get from the trained model. So the model generate this output, predict the word, and going to talk out. That's all. So that's the task here. So now we have to do certain pre-processing signals. So if you see, this is 0 to 1, 2, 3, 4, 5, 6, 7, 8, up to 10 seconds. If you go back to that audio clip again, for the first audio clip, so what is this? So now how many words are there? How many words are there? So how it's possible? So if I'm not going to say the same phrase again, right? So I'm going to say print my papers. So if I write, it should read. But here the print something is there. So that means we can't upload the spectrogram as it is. What we need to do is we need to break it into pieces. This 10 seconds, earlier also, we moved our window through the voice and break it into spectrogram, put it into the input, get the output. So now the text are there, but the spectrogram have a lot of words. So now we are going to break the spectrogram into pieces, right? Then that is going to be the input. Then we can break word by word. And there is another problem. If we don't know, print this paper. Print is a short, is shorter than that. Paper is little long, right? Print this paper. So how we are going to break it? So that we don't want to care. AI will do that job and it will do that thing. So that means while training, it will be able to understand those stuff. So now we can upload this smell spectrogram as it is to 10 seconds, because if we upload these as it is, the model cannot predict for different words at all. So we need to break it into pieces. So that's what we are going to do over here. We are going to break this smell spectrogram into a certain pieces, small number of pieces, and we are going to get the smell spectrogram, right? So now all these saved data over here, downloaded data, will be in this format, right? In this spectrogram format. In time is in seconds. But now what we are going to do is we are going to break it into millisecond pieces, right? So multiple milliseconds combined together, a word, right? We will see how the breaking input is going to happen. So now what we have done is we have 13,100 data. But if I load all the 13,100 data, this will crash, right? So what I have done, I have only taken the first 1,000 samples, the first 1,000 audio files, and the first 1,000 text files as well, because we need the text file also. So the first 1,000 audio files and the first 1,000 text file, corresponding text file. So I took that thing and I saved the data. You can see it over here. All these things are in this thing, right? So now I break it into small pieces and I save the data. So now check how many time steps are there. Okay. Basically, let me get that thing, time step. Okay, we don't want that code actually. So let's come and define. The time step is not defined, Kayla, it's coming, but it's fine. All right. So we'll go to that next thing. Let me see whether we have the time step over here. Okay. So now keep this one. So we are breaking into small pieces. We will get back to that point again. So now we have break it into small pieces and save the data in the save data file, right? By executing this folder. So we are going to take first 1,000 samples, audio clips, and the text file, relevant text file. We are going to break the spectrogram into small pieces, and we are going to save it over here as a spectrogram. So if you see, this is not a wave file. The save data is in NPY. That means it's a spectrogram. Those are numbers, right? So it's a spectrogram. We break it into pieces and we see. So now we will load this spectrogram. What the thing? Is it reset? Are you getting there? Same, right? Give me a sec. File path, okay. Give me a second. Let me figure out. Oh, okay. Okay. Yeah. Right. Give me a second. That's the issue. There was a formatting error. Give me a second. Give me 2 minutes. Huh? Okay. There was a name error. Okay. I'm going to upload this one to the drive again. Right. So go ahead and load that new tutorial. Okay. So under the text to speech, I'm going to edit and upload. Give me a second. See. Okay. Now you can go ahead and open it as a new thing. Okay. And run the first code. Sorry about that. You have to download it from the beginning. Run the code from the beginning. Can you upload? Open the new uploaded thing. Text to speech. Here. So go open this up again and run the code from the beginning. Install the pip install TensorFlow. Then download the data. Close the current one and open that one. Give me a second. Wait. It said saving failed. Give me a second. Don't open. I will upload it again. Sure. So what happens with the Google Colab is, yesterday I did the changes. When I saved, click saved and copied, but it did not save. That's the thing. So now the same thing happened now also. Now it's okay. You can open it. Go, close your current one and undo that. So the saving option is an issue over here. So that's why that error came. I changed that name, but it didn't get changed in the code. It was not saved. Now it's okay. We can go ahead now. So run, sorry about that. You can just go install the library download the Kaggle data and unzip it and do that metadata again, download it. Then after that, come and play that thing. Then come to this time and frequencies plot and again the MEL spectrogram. Right? Up to this, run it again. Before pre-processing audio and text data for speech recognition, just do that. Is it running? Yeah. Run up to this. Pre-processing audio, text and text data for speech recognition. Error? You cannot open it? Huh? I will ask it to open. Yeah. You already downloaded the thing. So rerun the code until this point. Generating and visual, sorry, up to this point. Pre-processing audio, text data. You have to get this one and you can wait over there. So what happened was the error is here. In the previous code, the name I changed it yesterday and saved it, but it not got saved. So that's the issue. So the name format. So in my thing, you can see in the save data, the first time I saved, did the feature extraction and saved, this is the name format it came. This is the name format it came. See? This is the name format it came. But when it's come to later, now I added this MEL thing. So I changed it to the current format. So it's overwritten over here. So for you, it will come as MEL 0. So after that, it will be okay. So run up to this point.
Then the same but obviously there are completely not I'm sure it's to understand the basic concept we are doing. So if you want to train a text to speech model from the scratch, which can work perfectly, you have to hire a GPU also. It's because it's all the text to speech the same, right? As the same concept of mentioned that is the proper manner. Is it working with the word also? I don't think so. I'm not sure. I don't know. If they have trained it based on word things, it might work. So certain things will say a plus sign. So when you read 1 plus 1, rather than reading 1 plus 1, they say 1 plus sign 1. Because that's how it got trained for that. You get it? So that I will try it out there. So I need to check how they describe that. So what the graph can be done is, so you now these generative AI and ChatGPT, you put an image to the ChatGPT and the image will be transcribed into a text. Right. So that text can be translated as the text to speech, right? To upload it to the GPT and ask what is that, then the GPT will use that. Text to image description. I can show you. So how the graphs can do it right now. Okay. Sorry. Let me go and found out some images over here. Maybe this image. Let's see, Sigiriya. Else I can copy and paste it also. Okay. We'll go to Gemini. So now if imagine this is a graph or chart. So what will happen is it will go and get this done. Staircase leading up to the summit Sigiriya, giant rock person in Sri Lanka. The rock formation rises from the surrounding forest, which is lush and green. This will be read in the text. So I think they do need to do something. Otherwise, image transcription, that you call image transcription. The Gen AI do it very nicely. ChatGPT do it better than Gemini. So now I have lost the free credits of 4. So it's not coming up. Okay. So have you got up to this level? Cool, right? So we will start. So what we are going to do is now, this is a big signal that we have. So now we need to break it into small pieces. Otherwise, the model cannot understand word by word. So we are going to break it into small pieces and we are going to save it in the saved data, right? So earlier what happened? The name error. If you go to the previous code and see, the name error mentioned over here is different. When I go to the next thing, the name mentioned over here is different. So that's what the error found, the file not found. You get it, right? So now I change the name over here and running it. Now the data saved successfully, right? So if you go to the saved data, you can find out these things. See here? All right, cool. Mel 0 and pi, mel 1 and pi, like that, your data should be there.
So it's, if you load it here further, it will come up. So earlier I have saved it in this format and execute other codes in this format, name format. So they're happy. So now I rechange everything. So now it's totally fine, right? So now we are going to do load the MEL spectrogram. We have break it into small pieces. Keep that in mind. Here the time is 9 seconds, 9 point something. Here I'm going to load the spectrogram from the saved data, the first 3 of them. I'm not going to do for the rest, the first 3 of them. So once you load it and plot it, the text example over here is printing in the only sense which we are at present concerned, differs from most, if not from all the arts and crafts, blah, blah thing. This is the text, right? Now you can see the MEL filtered bank in text. So from 0 to 70, I changed it into an index format. Earlier, this is the magnitude. I changed it into an index format, right? So that is a way of making that one. And the time is the important thing. Here you can see 10 seconds over here. I have break it into 800 and certain seconds, or like maybe nanosecond. It's not a linear scale, maybe millisecond, 1 millisecond, 1.1 millisecond, something like that. So I break it into that. So the breaking happens in this format, where the saved format, yeah. So SR is 22,000 and 050, NF50, all these things, hop length 256. If by changing this one, you can get the output with different lengths, right? So I just created the output in this format, but this is not right. But why I'm going to say it, we are going to listen to the spectrogram again and see the difference, how it's going to sound like. So the way I break it is not good, right? So it should be a different way. So previously in this thing, I have thought of teaching you the transformer architecture for the training, but realize it's too much. So last week only, not day before yesterday only, I worked on this and build this one. So this is a simple format. Transformer thing will go in the later stage, right? After I introduce to the transformer architecture. So now this is the MEL spectrogram. So the size is 80. This size is 80 into 832, this size. We are going to come to the second one, second audio clip in being comparatively modern, right? 80 is this size and 164 is this size, right? Earlier 832. Earlier the second clip is 0.1 seconds or something, right? The audio clip over here, the second one. If you go back and play it one to the second, what is the second audio clip? That is going to be close to 0.01 something, right? What is this? 0.09. So if you go here, you can see the same here, which is 10 minutes, 800. This is 0.01 or something. Break it into 160 time and small pieces. And here also again close to 10 seconds. So it's break it into 833, right? So now if you see, the y-axis the same length, 80, right? But the x-axis is varying. Time is 800 here 160, and here 832, here 833. So, but in AI, we need to have the same size input or output, right? Otherwise, we are going to have a mess. Do you remember? We took an image for training car, lorry detection, and we resize it to a same size, right? Because the size of the input is important for the AI network. Otherwise, it won't take the input. So the same thing that we are going to do, and we are going to resize the spectrograms into a same size. Then only the predicted spectrogram will be in the same size. Otherwise, we cannot. So now, before that, let's listen to these 3 audio sounds. So you have already we have seen it earlier, 1, 2, 3. Now let's see how these 3 things are going to sound like. converting MEL spectrograms to audio waveforms and playing them. Okay, so that's the task over here happening. What is the issue? Okay. So why I am saving these things? You don't want to save all the things over here every time. Why I am doing it? Because it's a loading model. It takes time through the NumPy. Sometimes this system crashes. Then restart. If you hit restart, you have to go back and again do the thing. So every step I am saving. So once I save it, even it's crashed, I can load the data from the saved data. Right? So that's the main purpose. Otherwise, no point of saving. You can run all the things in a shot in your computer. No need to save and load the memory. So now we'll listen to this first audio. First audio, we will go here. Right? We'll go here and listen first. Okay, maybe I'll copy this one. Okay. Back to back, we'll listen easily. Right. I'm going to place it here. The first audio, I'm going to listen. This one. I'm going to play it now. Okay. Now the same sound after plotting the MEL spectrogram into small time pieces, how it's going to sound. Because now it's small pieces. Break it. Even one word can be broken into 3 pieces. Get it what I mean? Right? But if you carefully listen, you can listen to the words. Again, I'm going to play. Printing. Reports from most, if not from all the arts in fact represented in the exhibition. So you get it right. So that's why I said the breaking I have done over here is not good. Right? So we have to carefully find which is the thing that we have to use by analyzing the audio signal. So the second signal, let's play and see. The second signal is a very small one.
In being comparatively modern.
Let's listen to the breaking thing.
In being comparatively modern.
So now what is happening? Multiple small pieces connecting together and it's reading. You are getting what it's saying. Comparatively, comparative. So phonemes, basically, right? Phonemes. Cat, C-A-T, K-A-T. Similar to that, we are breaking into small pieces. Let's listen to the third one here.
For although the Chinese took impressions from wood blocks,
right? You're getting it, right? So, okay. So that's reading speed. We can actually change it over here, the frequency, the thing. So that's fine. But now what we have done, we took a spectrogram, break it into small pieces, and we got these things. Because in the first spectrogram, 9 seconds, but it's a lot of words are there. So now we are going to break even the words and going to concentrate on the phonemes. Okay, cool. Got that thing. So now what we need to do, we need to resize because here 833 in the x-axis, here 160, here 832, not good for AI model. So we need to resize it. So I'm going to resize it, all the models, and I'm going to save it in the folder called resized data. There is no need to resize data, save it. I'm saving it because upcoming columns, it might collapse. So now I'm going to resize it. So resized spectrograms and corresponding text saved successfully. Cool. That is cool. Okay. So you can close it up and open it up and see resized data. So you can see all the resized data in the same name of MEL0, MEL1, MEL2, MEL3, blah, blah, blah thing, right? So let's now load this thing, load the resized data and plot it. The first 3, 1, 2, 3. See, this is the resized spectrogram. The resized, I have made it to the size of 80 and 863. The spectrogram is going to be changed to 18 to 863, right? So that's the thing now. So I'm going to play that one. If you carefully listen, you can listen to the text as well. So what is happened? 863 now, early 832, it got little bit stretched. So it's slowed down a little bit here. This is worst. Why? Because 160 change it into 863. Not bad. 863, 33 change it into 863. So how we can avoid that? We don't want to do this actually. If we have all the clips in the same size, 10-second size, we don't want to do it. We don't want to stretch it. We can just go as it is. Break it into small pieces, take it, we don't want to resize. By resizing, we are losing the clarity here, right? So while collecting the data, record it for maybe 2 hours, 3 hours, take a recording 5 hours, then break it into same size audio clips. So what the problem in our data that we have is the audio clips are not in the same size. So then we break it, when we resize, we make the clarity issue. To avoid it, while doing the data collection, collect the data at the same time sample. 10 seconds means all the data clip 10 seconds, then the thing is ready. You get it, right? Otherwise, the resizing will lose the clarity. Even in the image, resizing will lose the clarity, right? So that's the thing. So that's visually we have seen it, and audio also we have heard how it's losing the clarity. So now where we have prepared the data, and what we will do is we will load the data from the resized data. We will load the data from the resized data because I have saved all the 1000 data here with the text and everything, with the MEL spectrogram and everything. Now we have this data done. Then after that, once you play it, the data will be loaded successfully for this training from the saved resized data. So now we will say what are the size of these first sample, 80 into 863, 171, the text input size. Then if I say MEL specs 1, and this is 1, the first sample, second sample. So that is also going to be in the same size, should be same size. If you say 100 sample and 100 sample, it should be in the same size because we have resized, should be resized, and maybe 1000 sample, it will say no, nothing, because we have 0 to 999. We have totally 1000. So the 1000 sample ID is 999. So even the 1000th sample audio clip have the same size. So that means we have resaved the data for the training into a same size. That is very important. Otherwise, the AI cannot do. Even the image, whatever the things that we have done in the past, we do the pre-processing to resize, normalize, resize. So those are standard practice. So now skip this one. We don't want to do this. I just added. I just commented it. And we will clear the Keras session. I have added this over here because yesterday I tried multiple model construction to do the training, but the training failed. But what happens? While you do the training, in the middle, the training fails, all the weights saved data in the cache memory. In the RAM, it will be saved. So when you run a new training, that data will be there in cache and it will run on top of that. So the new memory uploaded, RAM crashes. So to clear everything, I have added, but this is not needed all the time. Since it's a loading tutorial, so I have added this part over here. So now we will construct the neural network model. So now the thing is important thing, the text. Give me a second. Where is the text over here? Here. Yeah. How you have to give the text into this model? Can you give a text as an input? We know neural network only can work with numbers. Right? As I told you earlier, we are going to give a text as an input. So how we are going to give the text as an input? So how we generated the text output? Do you remember? From the voice to text or speech to text conversion, how we have generated the text out? We give a word and we gave a number to each word while training, right? So the prediction is the number, then that number is correspond to the word, that word is printed over there, right? So the input also should be in the same way. So we have to give certain numbers to this thing, right? Printing one number, in number, the number, only number. So that is called tokenization. Tokenization. We have to tokenize it, right? So this tokenizing word you will hear in the generative AI. When you upload a PDF and you have to ask the question from the PDF, what it do is it send that PDF extracted words through a tokenizer and generate the output as a matrix. When you input a query, what is mentioned in the PDF, that thing will be tokenized again into a number and it do a search, semantic search in the numbers and find out that certain information from that chunk, then get back to the word. That's what happened. So that is called tokenization, or we call it as vectorization, right? Giving number to each word, right? So that is what we are doing here in the tokenizing part, right? Tokenizer part. What is that? So actually this tokenizer is giving a certain number to each word. There are different type of tokenizers, right? So vectorizers. So for example, if you see LangChain tokenizer, or there is another vector library. So they uses different tokenizers. So the important thing is if you tokenize it using one library, your question, queries, everything should be using that tokenizer library. Otherwise, number mismatch will happen. So I give the word number 1 for the, another tokenizer can give 10 for the. It's completely different on their architecture, right? So I'm using a pre-built library over here for the tokenizer. So now, and I'm going to build the model here where tokenizer and load the MEL spectrogram, okay, and load, sorry. Yeah, I'm going to load the data to the thing, right? So that is done. So here I'm going to do the tokenizer part. After that, tokenizer is tokenized and we have loaded the data. So we cannot purely load the data as a text because we are going to load the data for the training. So we have to give a number to each word, tokenize it, and we have loaded. So now we have a chunk of tokens, numbers through the tokenizer, and we have the spectrogram, which is in the same size. So input is the token, output is going to be the spectrogram, and we are going to do the training with the available spectrogram. We are going to give the token, predict the spectrogram, calculate the error with the existing spectrogram, and come back and train it. Giving the second token, get the spectrogram, get it done, and come back like that, right? So that's how the training. So input is a token word, output is going to be the spectrogram. So that is the reverse way that we are going to do. So now we loaded the data and we have seen all the data is in the same size. And now we will create the thing. So this is the neural network that I have done. But here you can see this model is a sequential model. Embeddings is the thing, vocab size, output embedding dim, and input length size max sequence length. So this is the word embeddings data. That means that vectorized data, 0 to 1, which is the largest sentence. So that many neurons are here in the input layer. And the output is going to be the dense thing, MEL spec shape. So it's going to be a thing. It's not a neural network single neuron. It should be a 2D thing, right? It should be a 2D thing. So MEL spec shape means the output is going to be in the shape of 80 into 863, right? Input is a token, 0, 1, 2, 3 neurons, flattened layer. Output is a 2D layer. Then only we can predict the spectrogram. Earlier, how? Input is 2D, output is 1D. So we get numbers out. Now the input, we are going to give the numbers for the words. Output is a 2D output, which is going to be the MEL spectrogram, right? So now we will construct the model. This is a very, very basic model, not at all equivalent to the basic version that they have first built. I have created this because to show how it works, right? But we will show a highly advanced version later. So now this is the parameters. Embeddings are this one, and dense is this one. So total parameters are this one. So 80 into 863 should be the dense layer size. 80 into 863. 80 into 863, 69,040. So that is the size of this one. So for that, this many parameters need to be tuned, right? 80 into 863. Yeah, reshape. That's the thing. So we are reshaping this one into this thing to get the spectrogram. So now we will do the training. Let's do the training for 5 epochs. I hope it works without crashing. Sometime it may crash. Last time it crashed several times. Let me see whether it works or not. I just running for 5 epochs to show the training concept. Let it train. Maybe we will run it for 20 epochs. Yesterday the output is not there. So change it out to maybe 25 epochs. Let's see. I hope it won't crash. Okay. We'll go to the restroom and come. So run the training. Let it run. And the website is 10. So the sample is loaded up and very small. Batch size is 10. We divided batch size is 10. So we have 1,000. So it's 9. Because 1,000 total sample, validation split 0.1. That means 100 sample will go to the validation. Rest of them are 900 sample. Batch size is 10. So 900 divided by 10, 90 per batch. Clear? Yeah. That you can see the loss is 73 point something. Is it reducing? Not at all reducing. Eh? Yeah, it's not a good model. It won't reduce. It was a very small compact model. So this is the worst model you can train in this lecture series. Okay, why? Because If you try to construct a large neural network, the Google Colab crashes. So this is how they do it. There are transformer architectures. There are many other architectures. Only up to this point is the same. Up to this point is the same. They do the data processing, everything, load, tokenize, and vectorize, do the embeddings, and get the input ready, input output ready for the training. Then the model architecture will be completely different, right? So I can show you something while the training is going on. Transformer-based ETS model. Images. Let's go to images. Yeah. See, this is another thing. Speech encoder prenet, text encoder prenet, speech encoder that comes. So these are different type of architectures are made. For example, another architecture. This is the text, 3D convolution neural network layer, bidirectional layer, and this is a spectrogram decoder. And finally comes up, go here, the final prediction will be the spectrogram, right? So these are transformer architectures. Even here you can see encoder, decoder, then the spectrogram. There are different architectures are used for speech to text to speech, but the pre-processing step up to now, those are the same, right? So we will learn about this transformer architecture, this kind of things, because the transformer architecture is the backbone of this ChatGPT, right? So it's a kind of a deep learning network, CNN based network, but it have multiple layers, attention layer, decoder, encoder, which keeps the memory while training. So it's better performance. So nowadays, earlier there was a trend in the research. So when the deep learning introduced, all the researchers, including image detection, classification, error detection, fault detection in power system, fault detection in machineries, all these things were done by machine learning earlier days. When the deep learning came into action, researchers took the same research with the same data, applied deep learning models, and showed machine learning took longer time for us and the effectiveness accuracy is very less. By applying deep learning models, this improved the accuracy by this many percentage, right? So there are a lot of papers published like that in the world. Machine learning, now deep learning. Nothing changed, only the neural network architecture changed for the deep learning. Now there is a trend, deep learning already done. Everyone is taking, okay, deep learning giving 95% accuracy. By applying the transformer-based architecture to this model, it's giving 99. Something like that, right? So the same research, now manual, then manual to machine, then machine to deep learning, machine learning to deep learning, now deep learning to transformer architecture. It's also a deep learning method, but adding the transformer architecture, the same research, they are showing, publishing papers like hell, right? So that's a new trend. Even I am doing that same thing in my university. Earlier did a couple of things from machine to deep, now deep to transformer. This time deep to transformer. But there are many models about to come in the future. So then the research will go on. Right, now the training is done, I believe. Yes. So loss is 73. The worst model you can train because this loss function and everything are very common. So never mind. And we will save the model. Take a while to save the model because, yeah. Then after that, you can predict the spectrogram and play the spectrogram and listen. Play that executed code, okay? This will take some time and this will take some time to predict. After that, you can play it out. What is the word? So you can say, welcome to AII here. Okay. This is the model. You can sample text. You can put it over here. What need to be read, right? Once the model is saved, run it out. It will predict a spectrogram output from the wording input, your sample text. So why I am saying sample text? I'm using the tokenizer to tokenize that words into numbers, and that is a maximum sequence length. If I don't have a maximum sequence length, what I do is I add 0, 0, 0, 0, because I have to match the input size. Ne? So I have said printing is the blah, 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 blah thing. That is 100 and some 71 words are there. But let's say I want to go to my home. It's a less number of words. So, but to add that thing, I have to add some zeros and make the length equal to the input size also. So now I made it. Now let's predict and play this thing to this thing. Let's listen. I hope you will hear a noise, something like that. We'll see. Nope, you can understand, right? What is the reason? Okay, you play it out. Let me go. Change it to a big sentence and read it sometime. You might get some words. Okay. Let's put a big word. We'll go to this metadata. We will expand this one to the chat GPT. Okay. Okay. Copy, paste it here.
and maybe a couple of words. Okay, let's determine the MEL spectrogram for that thing and see how this works, whether it will be able to identify or not. Because the model is very badly trained, because you can see these accuracies are not good. But the purpose of this tutorial is to show how this works. So the next part in that speech recognition, you can go here, load this text to speech using GTTS. So there I will show a pre-trained library, how you can use that to Python. Okay, the way they trained, the model architecture is completely different, but it's a pre-trained one. Right? Whatever you say, it's going to be the same, but it's not good. So we will go back again, text to speech GTTS, open that one. So now it's clear, right? How you do the training for the speech, text to speech. Is that clear? Cool. So now GTTS is a transformer based architecture, which is trained model by Google. The Google uses this model. So where you can go and install it first. So when you install it, it'll ask manage session and everything. So you have to go and cancel the previous session and close it. Then you play it out. Right. Then it will install it over here. So this is a GTTS library. I will say GTTS documentation. So this is a GTTS documentation. If you go here, you can find out. There are a lot of versions over here. And the language that they have used, where is the language? So there is English, there is France, and there is Mexican, Chinese, and everything. See, here you can find English Australia, English United Kingdom, English France is there, and China is there, Portugal is PT, Spanish is ES. So these are the code words. So once you go and install it over there in this speech to text model, right? Right. Let me save this one. Yeah, speech to text. This is installed. So this is just calling the library, nothing else. It's a pre-trained model, right? So you installed it over here. This is 2.5.1 version. Then you can change the versions also. Then text to say. Okay. Let's see. The language is English, EN. So if you go here, you can define the language EN here. Then come back and play it out. So the text is going to be played. So now we can say.
This is a simple piece of text ready by AI tutorial.
Clear? Okay. So similarly, I'm going to change it into a France and going to read this thing. So what do you expect? If I put France, the same text, the same thing should come, right? So this is the same text.
This is a simple piece of text ready by AI tutorial.
Clear, right? So if I put the French language over here, the same English text, what's the difference it's going to happen? Listen, that's why the Google is smart, right? Now,
This is a simple piece of text ready by AI tutorial.
now what Google have done? Tell me. They have asked a French person to read the English text, recorded the audio, right? Then created the sample, then trained that model for French. Right? You get it, right? Yeah. So now this is Chinese.
This is a simple piece of text ready by AI tutorial.
See, yes, Spanish, I think. Yeah, we can clearly say it's Spanish. Yes, Spanish. And for Chinese, I think it's a set CHN maybe. You can change it here.
This is a simple piece of text ready by AI tutorial.
You are getting it what is happening, right? So if you put into the Chinese text, let's get some Chinese text. That will be also perfect.
此代码片段演示了如何加载预先训练的神经网络模型。假设 model 下划线 saved 之前已保存。使用分词器和最大序列长度预处理示例文本，并使用加载。
You get it, right? So that's one of the model which is available in the Python library itself. So if you are working with the Python library, you can take it and you can use this model. So how it's trained? The same approach that we have done. The model is different. This model is going to be different, right? So this is one model just to show you how the training happens and it doesn't work. But these models, different model architectures have been come. But the idea is simple. You take the input, tokenize it, put the embeddings, input. Output, you are going to get the histogram. And the histogram is converted back into the audio. Clear? Right. So that is the concept of text to speech. So any doubts on that thing? So you can use this library for any other Python projects, whatever you want. Clearly, there are many other libraries you can install manually also for the new, like 2022, 23. There are a lot of transformer-based architecture libraries came up. You can use them. And even ChatGPT has their own one, text to speech and speech to text, using their traditional thing, which carries the emotion as well. So those are the things, right? So you can try those out in the thing, but the concept is the same. This is how the model training is done, right? Okay. So now let's go back to our AI tutorial. Week 10. Week 11, but we have, I think we can go to the transformer-based architecture. Let me see. I forgot. NLP, natural language processing. Here we will learn about the tokenization and everything. Natural language processing, where, for example, how the chatbot works, chatbot works. So when you ask a question in the chatbot, how it answer your question? Basically, it get your question, embed it as a vector, right? And go through the whole vector embeddings. Do you remember that we have done for the face recognition? We have put it as an embeddings, our features. When you take a new photo, embed it and match it with the existing embeddings, right? Existing embeddings. Same approach, the NLP based chatbots, you have all the information as a text file in the embeddings format, right? In the embeddings format. And you have your query. Okay, I need to know what is the course fees for AI program, right? So then it will put it into an embedding format, same embedding format, go through the text and match with the embeddings. and find out certain embeddings chunks. Okay. Fees, course fees is one material name. So wherever the course fee is mentioned over here, it will take those matches. And first 2 or 3 matches, highest matches, will be sent to the ChatGPT. Now, generative AI. So the generative AI, I know this is the question with the chunks. These are the relevant chunks of answers found out, right? Then you put it to the ChatGPT, and the ChatGPT is smart. It will identify what is the best answer for the question from that chunks. Then finally, it restructure and give it to you. So if you ask what is the optimizer function, that will be first embedded into embeddings, vectorized, and go through that vector store, your store with the embedding store, go through, find the matches here and here, select first 3 or 4 best matches. You can define that 10 matches or 5 matches, best 10 matches, and copy all the matches and your query, send it back to the GPT. And the GPT goes through that text and the query. Finally, it identifies the best answer, print it over here. Is that clear? So that's happening. So we will learn about NLP next week and dialogues with AI and everything. For example, I want to show you something under speech recognition. Texture recording, speech to text, text to speech. No. Where is that? Voice recognition, maybe? Yeah. Under voice recognition, there are certain embeddings, trained data, test data, Python, person identification. What I have voice embeddings and this one. I had somewhere. So there are certain tutorials where there, maybe I will show you the cloning, voice to voice cloning, text to voice cloning. So now if I want to get my voice matched to your voice, so what is the difference that I have to make? For example, so the spectrogram is there. So the way I read a text and the way you read the text is different, right? So I want to predict the word when I type something. I want a model to speak in your tone, in your voice. So that is happening. So if you take TikTok, there is Elon Musk coming and doing a podcast, but totally he's talking in his voice, but the context is totally irrelevant. He's talking like false information. But if you look at the video, it's really real, like because it's a podcast side view, you cannot see the lip sync and everything. You feel it like he's talking. And even I have seen a couple of videos of Ronaldo and everyone, they are talking something, right? But those are not real. He's talking about his son, saying he's expensive and everything, but it's not him. It's somebody typed and let him speak. But if you play closely, watch it, actually it's Ronaldo's exact voice. There's no issues. Then you type the text, that's all. So what happens is now, you shift that spectrogram, one spectrogram to his spectrogram format. That's all you need, right? Voice have certain features, right? So that feature is matched in AI, right? So you record my voice, his voice, put it to the spectrogram, identify the feature differences, and create a map between my voice to his voice. Then it's automatically happens. You create, it's not, you don't want to train. There is a trained model already. So you put your voice, it extracts your speeches from that spectrogram. You put a sample voice of Ronaldo, it extracts the spectrogram of that features and send through the model. It identifies the feature differences from your voice, his voice, right? And create a feature map. When you add a talk, it will give an output in Ronaldo's voice, right? It gets your voice, send through that map, create the Ronaldo's voice and spectrogram actually, then get the output as Ronaldo's voice. Simple, right? So the same thing, you can play with it. I couldn't find it over here. Maybe voice recognition. Let me a second. This is voice activity, voice embeddings. That is fine. Person identification using voice. That's a different tutorial.
Yeah, I will find it out. I had a one earlier. Maybe I'm not sure. Speech synthesis. Okay. So in the NLP, we will learn about certain stuff in the next week. Semantic analyzer. So and everything. So after that, dialogues with AI 2, 3, 4. These are building chatbots. So that person will come and teach you this thing. I'll be here, but he will do the lectures. Okay. All right. Cool then. Any questions up to now? 10th week, right? So any question up to 10th week. So if you see the concept is same. Only the feature engineering part is differing from application to application. But the way of training and everything is the same. Input output is different. But the concept, if you identify these basics. So for example, if I say, so okay, I want to build up a model. We have that tutorial, which can identify my posture. Sitting, standing. There are yoga poses. So this is this pose, this is this pose. If I want to make a posture recognition system, how you can build it? Simply you can say, you take different posture images, right? And name it as this posture, this posture, this posture. Simply you can send it to the model and send the posture, detect the posture text vector, right? Then whether check it out, this is or not, then do the training. So then when you upload any posture image, it will be able to detect. You think that is accurate? It cannot, right? Because you do a yoga pose here, background is this screen. You do a yoga pose in a park, the background is that one. But the model learning ability, we don't know. So you have to have yoga pose done in all the background scenery. Then it will be able to learn, okay, not the background scenery is the feature is the person pose. Tedious task. So what you can do? If you identify a person, body, and identify the limb structure, how many of you see the cricket bowling action nowadays? They analyze, right? So that is called Guyot pattern analysis. Guyot pattern analysis. So from joint to joint, what is the length different, what is the angle different, everything. So there is an OpenCV library to detect the Guyot pattern, right? So you extract that Guyot pattern from that person, identify the person body, using the OpenCV library, extract the Guyot pattern. Then you say this Guyot pattern is this force, this Guyot pattern is this force. Then the model will learn 100% accurate, right? So you do the yoga pose even in front of any place, like it will identify. So because it's only taking that feature. So what we do basically is we simplify the feature extraction way to show the model. These are the things, just learn it and do it. That's all, right? So even here, we did the feature extraction in a certain way using spectrogram, right? So that will be the part, the basic of it. And if you come across any problem, sit and think about what feature I can tell you to AI to learn. That's all, right? So it's like teaching a kid. Show an apple, show a peach. You want to show a difference. Both looks the same almost in the color and shape mostly. But you identify the thing. Okay, come here. If turn it down, if the bottom is like this is apple. If the bottom is like this is peach. So these are the certain feature in an apple you have to look to say with this or peach or thing, then the kid will learn faster. Rather than saying this is peach, this is apple. So the specific feature of an apple, specific feature of a peach, to teach the kid, this is the difference you have to look for next time when you are asked checking whether it's a peach or an apple. Clear, right? So the same way the AI you have to think about. If you want to enhance the model accuracy again and again, think about the feature. So that's why the feature engineering is important. Even though the deep learning came up, right? Feature engineers, deep learning, we don't want the feature extraction actually, right? But the feature engineers are highly paid still to the date now based on the problem. For example, we have did a problem for these one hotel forecast, right? Hotel forecast. How many guests are going to be there next month? How many food items are going to be sold next week? What is the revenue for tomorrow? How many workers are needed for next week? Everything we have predicted. But the problem, there were two companies selected for that kind of things. One is our one. So the ASCII who developed this platform. And other one is one AI famous company. I don't know, they didn't mention the name. That company portrayed themselves as an AI best company in Sri Lanka. Right? So we two were tendered out that project. They tried several ways to do that project. The output is a trash, and they withdrew from the project. They withdrawn from the project. They couldn't do it. They stepped down because this product problem cannot be solved because the data is totally irrelevant. If you put the data to deep learning, learn it and do it, it won't do. It won't do. So that's where the feature engineering part comes, right? So we did feature engineering for each data, identify the unique features, and we told the model, these are the features you have to look for the next prediction, right? So then the prediction worked successfully. Now they are marketing that like hell, right? So that's how. Knowing the AI is not the thing. You should know what can be done inside, right? So that is thing. So this is a very basic course. Advanced courses will be there in the future. So we will design, we can take you through what thing you have to think about for the model to learn. So the yoga pose detection, for example, I can learn the yoga pose, teach the yoga pose, selecting multiple different background sceneries and ask the person to do the yoga poses and name it as this is yoga pose 1, yoga pose 2, type 3, type 4. Train the model as we have done the character recognition. Same model, I can run that yoga pose will be detected. But accuracy, very less. 70%, 60%, not even closer sometimes. Right? But if you do the feature engineering, that means get the yoga pose, guide patterns, and do the training, you can achieve 95, 98%. Clear, right? So the guide pattern analysis are recent thing. Now in cricket, every ball they see the guide pattern. Okay, this guy dropped the ball. You can see the angle in here. Have you seen that analysis in the World Cup? They have performed the analysis, guide pattern. So at the time, Murali didn't have that guide pattern analysis. Otherwise, simply he could have told, okay, my hand is normally like this. See, when I'm doing, I'm bending a little bit. So done, problem solved. He have to carry a whole weight and do shit. But now the technology simply can identify they are chucking or not based on the guide pattern. All things feature engineering, OpenCV. We will learn about that, right? So now the concept is clear for the speech to text, right? Sorry, text to speech. It's clear, right? So the same thing is trained. So I have shown you one library. Simply, I thought of using the library earlier, but there is nothing to learn. So then I constructed the tutorial to teach you how the training happened, then introduce to the library, we can use it. Okay, Divek? Cool. Any questions? There is no question, then we can wind up. Okay. Thank you. Until next week. Bye-bye. Stop share.